In this session, before going to view the results, we will see how by hand calculation we can solve the existing problem. So let's discuss about that. This is our problem, and we have cutted the full problem into 3 sections. This cut is to establish the internal forces at that locations. Deformation delta is equal to PL upon E that we have discussed in last sessions. So the total deformation we can write down like this: delta 1 plus delta 2 plus delta 3. We have 3 sections, which is equals to summation of all the deltas from I equals to 1 to n, and which is equals to Pi, where Pi is the internal force, Li upon Ai. So this is the cut section 1 and applied force is 15 kilonewtons. So internal force will be P1, which is internal force, will be equals to 15 kilonewton in a tension. This is cut section 2. Applied force is 15 kilonewton here and 35 kilonewton here. That will give our internal force here, P2. So P2 will be equals to plus 35 plus 15, which will be equals to 50 kilonewton in tension. This is cut section 3. Here we have 15 kilonewton, 35 kilonewton, and again 15 kilonewton here compression, which will give here internal force P3, and P3 will be equals to plus 15 plus 35 minus 15, right? So minus is for compression and plus is for tension, which will be equals to again 15 plus 15 minus 15 get cancelled, 35 kilonewton in tension. So these are the internal forces or actual forces in the cross sections. So let's find out first primary variable, which is deformation. So deformation total is equal to summation of I equals to 1 to, we have here 3, right, which will be equals to P1L1 upon A1E1 plus P2L2 upon A2E2 plus P3L3 upon A3E3. So this is the first section, this is second section, and this is aluminum's third section. So the first section, let's find out deformation in first section. So the force in first section is 15 kilonewtons, 15,000 into L1 is 70 upon area pi by 4 into 10 square into Young's modulus of steel, that's 2 into 10 raised to 5, that's 2 lakh. For second section, the force is 50 kilonewton, so it will be 50. L2 is 90 mm, right, upon A2 cross section area of brass into brass Young's modulus. And for the third section, the internal force is equal to 35 kilonewton. 35,000 into length of aluminum cross section is 80 upon pi by 4 into diameter is 30 square into Young's modulus of aluminum, that's 71. So we'll get a deformation for each and every sections. So it's 0.0637 for this plus 0.1364 for brass one and 0.0558, which will be in total 0.256 mm. So we got the deformation U. Now next let's check out the stresses. So for the stresses, we know by using a strength of material equations, direct stress is equal to sigma 1 equals to P1 by A1. The first one is 15,000 for steel, and area is pi by 4 d square, which will be giving the answer of 90.98 Newton per mm square. As you know that Newton per mm square, this is equals to megapascal, right? So 190.98 megapascal. Sigma 2 is P2 by A2. So second section force is 50,000 newtons divided by area of brass, which is equals to 20 square, which gives me 159.1 Newton per mm square. Then third section is of aluminium, which has the internal force of 35,000 newtons divided by cross section area of 10 square, rather 30 square. So that gives me 49.5 Newton per mm square. So we got the internal forces 1550 35 kilonewtons. We got the total deformation of 0.2560 mm, and then we got the stresses also for each cross sections. Now let's do the last part of doing a reaction check. So the reaction will be plus 15 plus 35 minus 15, that is equals to 35,000 force, which will give a reaction of minus 35 kilonewtons. Right? So according to Newton's third law, every reaction has opposite and equal reaction. We'll not get a movement, we don't have any lateral force, and we'll not get any RCY reaction because we don't have any vertical force here. It's only axial force, so only actual reaction RCX will get here. So that's all in the hand calculation part. Now let's check that in answers also in the next session.